Okay, let's find the Taylor series for this function ln of x centered at not 0, but at a equals 2. So we're going to need the Taylor series. Let's write that down first. And here a will be 2. And again, I'm going to start taking derivatives to be able to get a pattern for this guy to plug in there. So we start with the function, and then we take derivatives. So first derivative is just 1 over x. Let's write that as x to the negative 1. Second derivative, bring down the negative 1, x to the negative 2. Third derivative, the negative 1 is there, bring down the negative 2x to the negative 3. Let's do a couple more. Negative 1's there, negative 2's there, bring down the negative 3x to the negative 4. And again, I'm not multiplying things out because I would rather see the pattern. Fifth derivative, negative 1's there, negative 2's there, negative 3's there, negative 4 comes down, x to the negative 5th. So it looks like I can guess what the nth derivative at x will look like. So it looks like if I'm trying to get a pattern, I have, again, this guy looks different, so maybe I'll deal with that guy separately when n is 0. I have stuff for all the way up to 5 and n. So when n is 1, I have positive. When n is 2, I have a negative. When n is 3, I have a positive. When n is 4, I put that separately as a negative 1. And then when n is 5, I get back to positives. And I wrote these guys because I'll have 1, 2, 3, 4 negatives, so yeah, that makes a positive. So this looks like a 4 factorial. This looks like a 3 factorial. That could be thought of as 1 times 2, which is just a 2 factorial. And this could be thought of as just 1, which is 1 factorial. So 1 factorial, 2 factorial, 3 factorial, 4 factorial. And if we want, we could put a 0 factorial there because that's just 1 anyway. And then at the 5th derivative, I have an x to the 5th in the bottom, 4th derivative x to the 4th, 3rd derivative x to the 3rd in the bottom, and so forth. So if I'm guessing a pattern, it's going to be, I'll take care of the negatives in a second. It looks like in the numerators, I have not n factorial, but n minus 1 factorial again, because I'm 1 short of the 5. In the denominators, I have the over x to the n. And then I have a negative 1 toggling back and forth. And at the first location, when n is 1, it is positive. So I'll just make that an n plus 1. So that 1 and 1 can give me a 2 and a positive. And then when I'm at 2, 2 plus 1, 3 could give me the negative there. But I'm interested in analyzing this now at a different center at 2. Is what I wanted to see what it looks like. So when x is equal to 2, all I got to do is plug in 2's for my x's. All the n's remain the same, only the x of course gets changed. So I get 2 to the n. So that's what I was in search of. And now I can have that go replace this guy over here. So let's go put that in. So I put everything in here, and I also had the n factorial in the denominator to account for. So all of that went for f of the nth derivative of f at 2 divided by n factorial x minus 2 to the n, and this is from 1 on, because remember when n is equal to 0, this guy looks different, so we're just going to evaluate f of 0, and that's going to be, or f of 2, I'm sorry, because the center was at 2. And that's just going to be ln of 2. It's going to look different than these guys. So ln of 2, we took the first term out by itself, and then everybody else gets picked up. The constant term is outside, everybody else gets picked up with the coefficients I found here. And this is just n minus 1 factorial. So those guys will go away. And I have my Taylor series for ln of x centered at 2. I also need the radius of convergence, so let's go figure out the radius of convergence. I'll use the root test this time, so limit as n goes to infinity of this entire thing raised to the 1 over n. So I'll eat up the negative 1 since it's going to be in absolute values anyway and become positive. I have 2 to the n, so that's going to be limit as n goes to infinity. This guy will just give me x minus 2. 2 to the n raised to the 1 over n is just 2 to the 1, and then I have n to the 1 over n. And as we agreed with L'Hopital's rule, that guy just goes to 1. So I have basically everything independent of n, because that guy just went to 1 anyway. So all of this is 1. So I end up with x minus 2, an absolute value over 2. I need that to be less than 1. So x minus 2 should be less than 2, which means the radius of convergence about the center 2 is going to be 2 for this one. Let's look at one more example. It says to use the Maclaurin series in this table, which basically just give us the Maclaurin series for cosine x that we proved in class. So 0 to infinity, we saw that it only had even exponents, x to the 2n over 2n factorial. So that's the Maclaurin series for the cosine function. At x, if we're using the table that gives us this information to evaluate this or to find the Maclaurin series for this guy, remember we said you could just use this idea that this box gets replaced by whatever you had there. So I can go and look at, quickly just recycle this result we showed. Negative 1 to the n, and box gets replaced by the argument of cosine here. Everybody 2n factorial. And that's pretty much it. There isn't much else to do. If you want to do a little bit more cleanup, you basically have pi over 8 to the n also, and x to the 2n, everybody over 2n factorial. And that's it. So if you already have a result, you can come up with the Taylor series or the Maclaurin series by just replacing what you see there. If you don't have the result, or if the directions say use the definition, then you got to go through the derivative analysis to figure out a pattern. And for the radius of convergence, you can always use the ratio of the root test.